Okay, this is example 2 from 5.3. I always like to call it the flat earth example because in order to really do this correctly with the information we have right now, we are going to have to assume that the earth is flat, which hopefully you're not in that board of assuming it is, but if so, that's okay. We can still do the math. A big advantage in these questions is to graph what's happening, or graph, I should say, draw what's happening. And really what's occurring here, it's going to be my rough kind of artistic skills. So there is a person standing on a flat earth, and some distance away, there is an airplane. And we'll draw kind of a bad, oh, I always get the wing wrong, but that's okay. There's my airplane right there. It does tell me that that airplane is maintaining a constant altitude of 6,000 meters, and the person is looking at the airplane. Now, the question, and this is really important that you're able to kind of look up there, talks about how the angle in question, which we're going to label as theta, is actually measured to the vertical. So that's theta. That's not angle of elevation, but in this case, that's the angle that we're going to use. Now, because we're measuring that to the vertical, there's a nice red angle in there. If this 6,000 meters is the constant altitude, then this is going to be 6,000 meters as well, and we will label the distance the plane is away as d. Now, from that diagram, we can use a bit of kind of classic right angle trigonometry and say that the tan of that angle is equal to the opposite side, which is labeled as d, over the adjacent side, which is 6,000. But it wants us to come up with an equation that relates d to theta. So really what we're looking for here, and function notation is an advantage, is we want to know what d of theta is. What's the horizontal distance if I can just plug in the angle that I'm looking at the airplane? So using, a surveyor's tool or something, I suppose, in real life. All we have to do then is multiply by 6,000. So I get that 6,000 times the tan of theta is equal to d, which means that d is equal to 6,000 times the tan of theta. Now, there are some restrictions on the angle. I hope logically that, again, because we assume the Earth is flat, my rotation is never going to go past the x-axis in either of those directions. So the only possible values of theta are right here, which is positive 90 degrees. And as the plane passes overhead, we certainly would mark those angles as negative 90 degrees. So before we get too crazy with our graphing calculator, it's important for us to recognize that theta only exists between negative 90 degrees and positive 90 degrees for this function. Although it is, oh, I messed up there, any real number within that restriction. Now, the reason why that's so important is that allows us to limit what we're actually graphing. Now, this is a constant, maybe not battle, but it is a hassle that in order to see this on the graphing calculator, what we are going to graph, and I'll just put on calculator here, is y is equal to 6,000. Oh, not 60,000, sorry about that. Y is equal to 6,000 times the tan of x. And we have to remember, as we evaluate this on my calculator, that x is representing the angle at which we're rotated from the vertical, and y is representing the horizontal distance of this airplane. And that does make this stuff trickier, is you have to be really, really clear and preferably explicit, write it out as to what your variables are representing. In this case, the question actually tells us what the variables represent, so I'm not going to actually write out again what the question already told us. All right, when we put that into the calculator and, annoyingly tweak our window settings, we're going to keep this in degrees. The question was in degrees, and we get a graph that looks like this. We see that we have the vertical asymptotes where we would expect. That's positive 90 and negative 90. And that's really important, that the next part of this question actually asks us to talk about, okay, what's going on here? So we've modeled the function, or modeled the situation by, the drawing I made and talking about the relationship between theta and d. We sketched the graph of the function. I mean, hopefully use your calculator. It's nice to get a particularly good graph. And then it says, see, where are the asymptotes located on this graph? Now, that in itself, I don't think is brutal, because there is no horizontal stretch, right? This x variable is untouched. So I'm going to put it back to theta, but we would know that theta cannot be equal to negative 90 degrees or positive 90 degrees. Now, it is important that, I wrote out these restrictions, and there's a really, really good argument that technically 90 degrees and negative 90 degrees are not valid because they are asymptotic. And that's the problem, that in the question, it kind of makes sense, but once you actually start to do the math, it cannot be those values. So we really should change that. That's an oversight of mine, but hopefully we fix that mistake well enough. Okay, what these represent, these represent the angles at which the plane is on the horizon. meaning that it looks like, the plane is on the ground. Although again, the Earth is not flat, so we would probably still be able to see that airplane in the air for several degrees past 90 degrees, depending on how high above we are in the visibility that day. Okay, for D, that's C, sorry. For D, it says, explain what happens when the angle is equal to 0 degrees. The plane is directly overhead. Sorry about the angled writing there. And that means that D, the horizontal distance, is equal to 0. And I'd like to point out on this graph, we do have that point at 0 degrees, D is equal to 0. Keep in mind that on this graph, theta is represented by the X quantity and D is represented by the Y quantity on our graphing calculator. Okay, that is, kind of a pretty typical TAN application question. You are not going to see a lot of these. Please don't stress the TAN function too much. I really do want you to focus on sine and cos because we run into them just a ton more. There's the textbook assignment for 5.3. Make sure you're chipping away at these, getting ready for that completion assignment and any assessment we have moving forward.